what it means, and then we'll talk about the main theorem in the field, if you like, in the context of stationary solutions. And then we'll talk about the main ingredient, which is used to prove the main theorem, and that's when we will need to remind ourselves from some of the definitions we had in lecture 2, in particular that of a killing horizon. I put it in brackets as Hawking's theorem because Hawking is the first to have proven a statement of this kind. I put it in brackets. I call it extension theorem because in truth, Hawking didn't actually prove the theorem. There was a gap in the theorem, and it was later filled in by other people. But it's that part of the history is not well known. People still refer to it as Hawking's theorem. Okay, so a reminder. I think for a reminder, I'll just speak. I mean, the reminder, quickly was that in lecture 1 we looked at definitions, right, which are important because they underscore everything. In lecture 2, we found that in the case of static, right, in the case of static vacuum, I shall just say all is well that ends well. In particular, what this means is that the static classification gives you Schwarzschild, and we're all very happy with this. Then what we saw is that we also saw that axisymmetry when added as an assumption also ends well. In particular, in that case, we get Kerr. So this is to say that under the relevant definitions, if we, in the category of smooth metrics, if we add axisymmetry as an assumption, then we actually get the classification theorem in Kerr. And so at the end of lecture 2, which was last time, I asked the question, how do we justify this thing, right? And this is now the subject of lecture 3, right? So in lecture 3, the plan is, right, the plan is understanding axisymmetry. When are we allowed to assume this, or can we actually justify this on the basis of other assumptions? Okay, any questions concerning what we've covered in the last 2 lectures and what's coming up today? Okay, good. So now let's just go straight into it. So smooth is F is in CK, rule K in the naturals. Okay, so basically you're infinitely differentiable. Okay, this is analytic. A real analytic function is smooth and such that its Taylor series at any point right, which we can write down as the following thing. converges to f of x. For x in a neighborhood of x0, and the convergence is pointwise. Okay. So now let me give you some examples of some functions which are smooth but not analytic. Right, so definition is here, and now we go to examples. Okay. So example 1, define f of x as follows. Okay, now that function looks like this. Right. It's smooth because I can differentiate it everywhere, but it's not analytic at these places, because at these places, the function, if I take the 0 definition of the function is 0 everywhere, so all the terms in the Taylor series are 0, and so it doesn't converge to, say, a point in a neighborhood of this point, say a point here, right? It's non-zero. Okay, similarly, another example. Okay, this is a function that looks like this. Right. So again, it's not analytic here, essentially for the same reason. Okay. Again, you can see it's smooth because I can differentiate it all I want, but it doesn't converge to its Taylor series everywhere. Okay, and then for funsies, here is a funny one. This is a function, a big f of x, which you can define as, in the naturals, okay? And then this function is smooth. To see this, you have to prove a convergence of the series that you get from differentiating this guy. But in fact, it's not analytic. But the reason this is a fun example is because it's actually nowhere analytic. So in this case, in these cases above, we could locate the non-analytic to a single point. In this case, this function is actually nowhere analytic. It's kind of a pathological example. So nature is not analytic, right? Or at least not that we can see. So you can do this in all sorts of ways. You can look at, I mean, if you wanted to argue it's not smooth, you would have to look at shocks and things like that, but not analytic. You don't even have to look that far. You can look at heat flow, wave collision. If you set up any data, if you set up any data, initial data as a bunk function, then from above, you saw that was not analytic. Okay, so assuming that the whole of space-time is analytic is obviously problematic. So now let's see what we can do when we.
When you say nature is not analytic, do you mean is that because of idealizations we've made in the like description of the phenomena, like generation of caustics and optics or something like that? Is it that we're getting singularities, or they're equivalent as a result of mathematical assumptions about the behavior of these phenomena, or is it a belief that nature itself creates these singularities?
Yeah, so again, things being singular is not of issue. That would be asking, that would be saying like nature is not smooth, right? And then we could talk about singularities. Analytic, the point I'm making here is that analytic is much stronger. Analytic is about the convergence of a Taylor series. And if you have any kind of function that looks like this in nature, where something stops at some point, it could be modeling, say, the gas in a star. At some point, the surface of the star, beyond that surface, there's no more gas, or it could be a neutron star, whatever. I mean, anything that involves these kinds of functions where something stops, and it doesn't have to stop in a sudden, discontinuous way. I mean, this is all smooth. Then you would not have analyticity. So it's not a statement about singularities, really. It's a statement about whether or not we can expand every function in terms of its Taylor series. So it's really a mathematical tool that we use, human beings use, to describe things. Yeah.
So when you say nature is not analytic, you mean is that the math used to describe nature is not analytic, right? This is a feature of mathematical functions of the world.
Yeah.
So I guess I'm trying to understand exactly what the content of that is. So is it that nature is not well described by analytic functions? Because it seems like anytime you're applying math to the world, you're doing some kind of representation that's not going to be perfect. And so what does it mean to say that
so
it's not well described by an analytic function?
Yeah, so I think that's a great question. So let me put it this way. So this is the mathematical universe. Math universe. Right? This is the portion of the mathematical universe that, insofar as we can tell, has been used to describe nature. Okay. Then is that
well? This is the tools that describe nature well.
Yeah, sure. Yeah. So like, we'll have like, we'll put in here like, PPTs, they're useful, groups, they're useful, geometry, that's useful, all the mathematical arsenal we have to do physics, essentially. Okay. And then if you restrain yourself to the world of analytic things, then you're essentially looking at something like this. Right? So you're saying, okay, these are analytic functions. Okay, so that's the point I'm making. That, if you restrain yourself to analytic functions, you kind of miss like basically most of all phenomena. So like dispersion of heat, collision of waves, setting up initial data, like solving evolutionary problems, etc. So certain things are analytic. Like for instance, we can describe the round sphere using an analytic function, but it's a very small subset of the kind of tools that we have to describe nature. So the assumption that black hole uniqueness can be proved using analyticity is essentially assuming that of all the stationary solutions that exist, they must all lie within this little square. That's essentially what I'm trying to mean. And there could perfectly be a stationary solution over here. Nothing wrong with that.
Yeah, so Marcus.
Yeah.
You keep saying that heat diffusion is not analytic. And yet, when I think of heat diffusion, first problem that comes to my mind is a Gaussian pulse, how it evolves with time. It evolves as, Gaussian with some similar properties. I think it's entirely analytic as far as I can tell.
Yeah, so what I mean by that is that, like, for instance, you can perfectly well solve a problem where you have like you can make perfect sense of say like a metal rod where you have a heat source that you switch on at time equals 0, say here, and then over time, this heat spreads, right? You can make sense of that problem, and it makes perfect sense in nature without the initial data being an analytic function. So in particular here, I would switch on the heat at some time where the heat would be in 0 before, and then it switches on. Moreover, there'll be a spatial region which looks a little bit like these bump functions, where beyond that region, there would be no heat yet at that time. And you can make sense of this evolution using PDEs, using all sorts of things. You can even do simulations on a computer, etc. Never have to restrict yourself to the realm of analytic functions.
Martin, I have a question.
Yeah.
So in Oppenheimer-Schneider, when you set up initial data for the star, if you assume the star is a finite, it has compact support in the initial data surface. You then assume that you're truncating the density of the star and it just drops to 0 outside, right? So this is an example of non-analytic initial data.
Yeah.
Yeah. So, but we know that we can use, for example, the Israel junction conditions, and we can match space and outside. So would you call this a problematic, would you call this problematic from the point of view of analyticity, or
yeah.
would you say so?
Yeah. Yeah, I mean, I think this is the picture you want to have in mind. Like, you got tools, they make sense. Analyticity is a very specific kind of function. There could be stationary solutions which are not analytic. There's nothing a priori that you can rule out there.
Also, just a follow-up question.
Yeah.
So in your reconduction problem, that's like setting up initial data, at least in this case, part of the analyticity. You're setting up initial data on a constrained manifold, sort of. Right?
Yeah.
So would you expect analyticity at the edges of the constrained manifold on the 2D space-like surface?
No. So like another example of this is like, your mug, right? Your mug, right? So your mug contains water or, tea, depending on what you like. Chai, perhaps. I like rooibos. There's a mug here, and, the water kind of goes like this. And this thing, the water profile here, is certainly not analytic. So if you try and describe this function, for the heat, for the water level, this is not analytic. In a gas, a star, say, you could do the same with if you have a star or some, compact body, typically, like you said, junction conditions, etc. Typically, as a function of radius, you will model the gas in some way. Maybe the pressure. So this is, let's say it's the pressure. Or let's say it's the density. You'll have something like, I don't know, maybe it's constant and it goes down to 0 or something. This function here, you don't have to restrain yourself to something, not necessarily analytic. Right? I'll just say not necessarily analytic. So you can pose the data as a non-analytic function, just as a smooth function, like a bump function here, right? You can do something like this, right? In that case, it's not an analytic function.
So in general, when you have have compact support, like whatever. You have boundaries, you'll have these sorts of issues. Okay.
Yeah, so I kind of see what you're getting at. You're kind of asking like, when can we expect this analyticity assumption not to hold, right? I'm with you. I think that certainly whenever you have constraints, like you have a container or you have strict boundary conditions, then you certainly should expect analyticity to not hold there. I also think that, and now this is totally speculative. It could be that the event horizon somehow, it could be that there are solutions somehow that are not analytic at the event horizon, or at some surface, some surface of interest. It could be. There are examples of non-analytic black hole solutions that are smooth everywhere, but non-analytic. They are Robertson-Troutman Petrov type 2 space-times created by Bichak Podolsky in the late 90s, early 2000s. They have a cosmological constant. They are similar to Schwarzschild de Sitter, but not quite the same. And they have a smooth, everything is smooth. Well, for some of these solutions, everything is smooth, but there's a breakdown of analyticity exactly on the event horizon. But examples like that haven't been made without lambda. So it's an interesting question. Can you construct, I mean, again, coming back to Ramesh's point, show me the money, show me an example, right? It's, if we did, we wouldn't be in this room. I know what you're after. I'll give it to you. I don't have it. All right, where are we? So that was analyticity. I think we had a nice little flowing discussion just now on analyticity. I'm glad we had that. Okay, so let's see. Where are we? Yeah, let's really go into the main theorem. So, okay, so this is going to be a bit of a mouthful, I'm afraid. Okay, so this is the best theorem we have when it comes to, getting Kerr. So these are the assumptions on the left. So you have analyticity, vacuum, you have some global conditions. This includes like all the things we've seen. So asymptotically flat, conformal compactification, smooth, etc., etc. You have a stationary killing field. You have a connected event horizon, and then you have this extra technical assumptions. It's either rotating or it's mean non-degenerate. Non-degenerate was the behavior of the surface gravity on the event horizon. So now I'm going to show you how this theorem is actually proved, so you get a feeling for the logic of where analyticity is used. Okay, so this is like, this is the classical no-hair theorem. This is like when people say no hair and stuff, they really mean this theorem, right? This is like the best thing we have, right? And this is not from the 60s. This is 60s plus 70s plus 80s plus 90s plus 2000s, right? This is like the full arsenal. Okay, so how do you actually prove this? Okay, so step 1, 2, 3 implies, yep.
Is there an assumption of the number of
Oh yeah, yeah. It's always 4, yeah. Thank you. So the first thing is you show that things are smooth, the event horizon is smooth, and the event horizon is S2 cross R topology. Then you use assumption 1, assumption 4, and conclusion of 1 to show that the event horizon is a killing horizon. So last time I defined what a killing horizon was, and now you see it come in at this point. Okay, and this thing right here is typically called, Hawking's theorem. And what it tells you is that you have a null killing vector field, null killing field, which generates the event horizon. Moreover, it's a killing horizon. So this is an important, there was a question by G. Weinstein in lecture 2. And the question was, what is a killing horizon? Essentially, the question was, what's the point of this thing? And the point is that it's because of this theorem. So this theorem tells you that something global is in fact something geometric. So an event horizon is just defined globally as the boundary of the path of non-infinity, and so on and so forth. But this is saying, actually, no, that event horizon is in fact generated by a null killing field. And that the cross-section of the event horizon is invariant under the flow of this field. So this is an important theorem. And what this does is that this splits it up into 2 cases. So you have non-rotating and you have rotating. Now, if it's non-rotating, you can actually show that it's axisymmetric. And this is again, whoops. This is again resorting to Hawking's theorem part 2. That's the $1 million question. That's Ramesh's question. Show me an example. Something stationary, not Schwarzschild, and not axisymmetric. If we had an example, we wouldn't be in this room.
I have a question.
Yeah.
So in your set to the proof, it's a 2+3 that you already used to cross article for the event.
Yeah.
So why do you also need connected for the event?
Well, it could be, this is the topology of the connected component. So they could all be S2 plus R. And then if it's non-rotating, it splits up into 2 cases. Either you have degenerate, or you have mean non-degenerate. The surface gravity is vanishing, like in the extremal case, right? A non-degenerate killing horizon is when it's non-zero, the surface gravity with the proportional, the coefficient in front of the vector field. Mean non-degenerate is just that when I take the average, it's non-zero. And degenerate means it's identically zero. So mean non-degenerate, then you have lots of work. So I'll put it in blue. Lots more work. Lots more work. And you get Schwarzschild. And then okay, and then degenerate, it's open. So we don't actually know how to we don't know how to get rid of this. we don't know how to get rid of this. So that's why it's an assumption that it's mean non-degenerate. It's believed that this is just technical. It's believed we can get rid of this, but we just haven't worked it out yet.
So when we say degenerate, we degenerate everywhere on the eye.
Yeah, it's identically zero. Yeah.
Mean non-degenerate is actually about the average.
Yeah.
But at the end of the day, it's like a constant gravity of the earth, right? Not assuming it, but partially this constant.
Yeah.
Gravity. So
Yeah.
it's a constant.
Yeah.
So not one of the assumptions.
Yes.
And the curve problem, also constant gravity.
Yeah. Surface gravity. Yeah.
The gravity is constant, but it was not hardwired into the constant problem.
No. Yeah, it's funny that the degeneracy of the killing horizon only comes up as an assumption in the non-rotating case. In the case that it's rotating, you use the part 2 of the analyticity. I'm going to show you how to get axisymmetry. And then once you have axisymmetry, you can go back to the theorems I showed you before in lecture 2, that if you're stationary and axisymmetric, smooth, then it's curved. So then, then you finish this, finish by lecture 2, right? Finish by lecture 2. Because once you know it's axisymmetric and stationary. I think, whilst I was a bit cheeky with Peter's question, I think I'm going to take Peter's question a little more seriously, just for a minute or two, and then we'll go back to the rest of this slide. No, we'll come back to it. We'll come back to it more seriously. But for the moment, let's just come back to it briefly. So I don't expect so there's two ways this theorem, there's at least two ways that you can have not curve. You can have a setup where something is somehow not analytic. So maybe the metric does something like this or something. So that's option number 1. Option number 2 is that it's like, it's not axisymmetric, right? Not axisymmetric. And then we get a Peter's question, which is, how could it not be axisymmetric? Well, remember that axisymmetry means that there's an axis of rotation. So if you have something that has it has some symmetry, but it's not exactly, maybe it's like, think of maybe like the pictures you see in the solutions to the Schrödinger equation when you solve for different energies, different number of modes, you see that there are kind of islands that form of where the electrons could be. Maybe something happens like this, where, this goes down and something is 0 in this region. Then there is a discrete symmetry, but there is not an axisymmetry.
The third is non-vacuum.
Oh, and non-vacuums already known. Non-vacuums already known not to be unique, right? Yeah. Peter, does that answer? How could it not be if you have a discrete symmetry like this?
Well, you're saying it's not really axisymmetric.
No, I'm saying you're asking for a situation where it's not axisymmetric. I'm giving you an example where there is symmetry, but it's not axisymmetric. Right, I'm giving you an example where there seems to be some axis in this picture, right? There seems to be an axis, but axisymmetry means that it's invariant under the flow. And if this line goes to 0 between these two orthogonal lines, then it's not a continuous symmetry, right? It's a discrete symmetry.
As you said, the situation of this kind of but
yeah, I mean, again, this is totally conjectural. Obviously, we don't know. If we did, we wouldn't be in this room. We would have, yeah, exactly. Yeah. but I'm just trying to, Peter's question is legitimate in the sense that, you want to kind of conceptualize like, how could this fail, right? Sort of what Ramesh was also asking. How could this not be a certain way? If you can't at least come up with a picture or a drawing or something, then like, what are you doing? This is the best I can give you. Sorry.
Okay, but I still feel a little bit hijacked in the sense that what you're doing is imagining things that are a little bit different from pure actual sympathy, and then saying, lo and behold, we can get something and that doesn't surprise me.
Yeah.
What surprises me is the idea that you have sympathy, and that it could lead to something. I mean,
No, that I think no. So remember, if it's axisymmetric, it is curved. Right? We proved that in lecture 2. Right. Remember, the whole point here is that in lecture 2, we showed that if you're smooth and stationary and axisymmetric, then you'll curve. Now the question is, how do we get rid of axisymmetry? So if you get rid of it, that means you're not allowed to assume it. So if you're not going to assume it, you have to prove it. And then the only way we know how to prove it is by analyticity, which is this problematic assumption. And so I understood your question to mean like, how, yeah. Okay, so how does analyticity actually come in? So if this is the analyticity is used in two places. It's used along here. Right, that's part one. It's also used here, part 2. So part 2 of the Hawking theorem the domain of outer communication curve. So part 2 of Hawking says the horizon killing field right, this vector field, either coincides with K which is the stationary one. So remember that K, let's draw a picture. So in this region, we have a time-like killing field, right? Okay. So either it coincides with K, so remember this is now a killing horizon. Or either or, the entire space-time contains an axial killing field. And axial means tangent to generators of SO2. Okay. So killing field M is axial if it's tangent to generators of SO2. So how is analyticity used? So it's used in two places. Let's go back to the colors in red. So first of all, it's used here, right? It's used this place, right here. It's used to get that the event horizon is a killing horizon and that you have this null killing field which generates the event horizon. There you use it. Then you use it in a second place here, where you say, not only is it there, but it extends throughout the whole space-time. And so that's why I say 1 and 2. So 1 is the red region is to show that this the event horizon is a killing field, right? It's a killing horizon. There you use it. But then you use it again because what you do is, well, in the original effort to the proof by Hawking, you say, well, if it's analytic, that means I can extend it. I can do an analytic continuation, and there's actually a unique analytic continuation which extends it sideways, right? So into the space-time towards infinity. That's where the second part.
Martin,
Yeah.
The thing that you're looking to write, is an assumption in part 2.
No, it's the conclusion of part 2. So it's the conclusion, right?
Assuming implicitly.
Yeah. So now, so we're coming up to the end. We should leave time for discussion. So now I'm going to give you the actual theorem, the modern theorem. Well, I should also tell you something which is important actually. So actually, I'm not going to give you the precise theorem because I've given you the gist of what it says, which I think is enough. What I'm going to tell you now is about something that's, I think, very intriguing and interesting. So it turns out, so this is going to be a remark. So it turns out that, so actually I'll make 2 remarks. So remark 1, it turns out that that under these assumptions, if the original killing field is time-like, then the space-time is analytic. And so what happens in Kerr is that you have this problem where in Kerr you have, this is, say, radius. You have this region, which is, you could call it the outer horizon, if you like. And then you have this region, the event horizon. Now, what's interesting in Kerr is that far away, it's time-like. The killing field K is time-like. But as you go in and you go into the ergo region, then it changes character, it becomes space-like. And so this is interesting because I told you, you want to get rid of the assumptions. And now I'm telling you, actually, if the killing field itself is time-like, then you can actually prove that the space-time is analytic, right? Which is kind of surprising. And so then you'll say, okay, so what's wrong with Kerr? Why can't I finish and close and say, okay, I can prove Kerr's analytic? Well, the problem is that in Kerr, before you actually get to the event horizon, you will know this, there's an ergo region. And this is where the causal character of the time-like, asymptotically time-like killing field changes sign. So although in Kerr it is analytic in this region, you can't prove that this would be true of any black hole space-time. So that's remark number 1. Remark number 2 is perhaps more, it should make you feel that something fishy might be going on. So remark number 2, the extension of axial killing field sideways. So in the Penrose diagram, that's going from having a killing field here. This is what I mean by sideways. The extension uses analyticity via a classical theorem of differential geometry. In particular, no Einstein equation. So this is, for the mathematicians, this is the biggest problem, because basically going from the killing horizon, which is the symmetry on the horizon, to a global axisymmetric spacetime involves using analyticity, but the actual proof is a theorem from the 1960s by a certain guy called Nomizu. And this is a theorem in differential geometry that if you just have a killing symmetry of an analytic metric, then you can extend this killing symmetry globally. So what I'm trying to tell you here is that this does not use Einstein equation. This is a very kind of classical mathematical result. Okay? And for a mathematician, that's fishy, because if you're proving something about Einstein's equations, but you're not using Einstein's equations for a key crucial part of the proof, then maybe you're doing something fishy.
There's things that you have a space-time system, but you have a global axial, or you have a axial field on the, you have a killing horizon which is there, and you're using analyticity, you can just do it, even if you don't assume that.
You have to have other assumptions like simply connected and a few other things, but yeah.
General theorem that seems like it's not true. I think you're going to lose less. Why the mathematician?
Yeah. So it's fishy because it's like, it's a bit like this. It's a bit like you're here, right? And you want to go to some house here where you have, some nice, nice meal or something. And, the honest way of doing that is by just, going there, whatever come maybe of say like a river, or some forest with some big mean, whatever. But yeah, giant spiders, etc. But actually, and so like the skills to go across here is to be like a good scout, so good like forest and river skills, say forest and river skills, right? River skills. But in fact, with analyticity, you just go above and you just land here, and this is what analyticity does for you, right? Analyticity. And then the skills you need to go to the house using analyticity is just a passport, right? Where you can just take like, this is your passport with your face on it, and you can just take a plane and you just get. So the mathematician thing is fishy because you're not actually using this thing, right? The Einstein equations, it should be a fact about the Einstein equation, certainly the vacuum Einstein equation, because that, for instance, when there's matter, these theorems are not true. So you should certainly use something about vacuum. The fact that it's vacuum, that should be a key assumption. But with analyticity, you don't even need to think about Einstein equations. Like if you had analyticity, you don't even need to care about Einstein's equations. They only answer in a very weak way. So that's why it's fishy, right? It's like using a trick which bypasses the whole subject, right? Bypasses the whole point of what you're doing. It's using a tool that isn't the tool you're supposed to use to get to the destination you want to go. Yeah, exactly. Yeah.
It is fair.
That's right. Analyticity feels like a cheat, right? Like you're supposed to climb a mountain, but you're taking a helicopter to get to the top.
And particularly if you like hearing stuff.
Exactly. Like by, and also that things will be analytic if the killing field is time-like, and that it changes character and care outside. So you're getting like signals that you shouldn't be doing this, and yet you're doing it. That's kind of the issue.
If you said that once you put pattern, you can violate the theorem.
Yeah.
But there was no, something about pattern in that theorem, the Japanese theorem that you mentioned.
Yeah. This is just Nomizu is just a very general.
So these factors, found examples, they are not analytic.
I don't know of any that are analytic. No.
That's the way to see, right? Even one of them is analytic. And, it exists, then obviously something is wrong.
Yeah, so in 4 dimensions, the only matter examples I know are like dust or certain like Euler examples, and they're smooth solutions, but they involve like constructing certain shells and things like that. I believe that.
Yes, that's right.
Yeah,
What's wrong with this? To me, that's like a perfectly reasonable model, but you're telling me that, oh, but analytic.
Yeah, I don't think, yeah, that's right. Those aren't analytic. Yeah. They're smooth, but those are all, so all of those are actually static. So they're all spherically symmetric. They don't actually rotate. I don't think we actually have examples of matter rotating, co-rotating with the black hole, where the solution has to fail to be curved. We don't have examples of those.
They're constructed models, like if you're doing matter is satisfying some sort of other things, like say, when there are these regular black hole solutions, for example, that people are constructed, which has some stress center, it violates some independently. It's hypersymmetric safely, and it's also
Yeah, but
it's really violating.
Yeah, I mean, once you violate energy conditions, like, I'm no longer interested.
Right. That's never went to
Yeah,
that.
that's right.
You
Yeah.
did say I must satisfy everything.
So remember, I'm in vacuum. The moment I drop vacuum and that I allow for matter, I shouldn't even expect these things to hold. I shouldn't even try to prove anything, right? Because there are examples of solutions. There are ones that violate energy conditions, but there are ones that don't violate energy conditions and that are not Schwarzschild or not curved. I just don't know what they look like in like how to write them down. I know the Schwarzschild, I know the spherically symmetric ones, but I don't think anybody's actually written down the ones that rotate. So people have proved that you can have solutions, but they haven't written them down. It's just an existence theorem. Whereas the spherically symmetric one, because it's easier to construct a function that's just a radial function, they've actually written down the explicit form of the solution. And this is for Euler Einstein. It's the fluid. And there's these shells of fluid that are around the black hole. But for rotating, they haven't done it.
The trick that you are telling me, right? The term knows how to take any spherically symmetric black hole and make a spinning cell out of it.
This is
Interesting.
this is Mustafa Sagan has a different problem where we sort of we work the Newman condition. And so you can create some static phase and stationary phase. So with the static phase and again the energy condition is important because the static phase may satisfy the matter generation static phase may satisfy energy condition. But not necessarily for the action.
Yeah, I mean, that's a problem as well, right? That's a problem.
In fact, I think our solution speaker today has two one with the regular solution.
Yeah, again, big problem. I mean, all this matter stuff is fine. Like I think in matter you can have something that's not Kerr, not Schwarzschild. I think that's fine. I think what's hard is the vacuum case where you just drop density, but you still have vacuum, and you're trying to get rid of you're trying to construct, I mean, we'll see this in lecture 4, but in lecture 4, I'll communicate some opinions of some of the leaders in the field, and they actually think that, there could be examples. And that it's just that they're unstable and we don't see them and they don't exist in nature, whatever, but they do think it could very well be examples. Yeah, let's wrap it up.
Thank you.
Thank you.